All right, here I want to mention just a few things about the CAD to FEM process. So typically users of Fine Element Method constantly face CAD issues, okay, computer aided design, and they cause meshing failures and have significant impact on the analysis times, okay? And this basically comes from overly complex or poorly defined or corrupt geometry. And CAD model features such as fillets, small holes, short edges, small faces, and other artifacts that are valid in CAD but negatively impact and constrain meshability. And it's not really even about meshing constrainability, meshability. And it's not even about just meshability, even just running a simulation. I've seen a lot of issues. Okay, and you see this in the primary workforce. So I can tell you where I see it mainly now is on capstone design projects. A lot of times the sponsors will throw across this great CAD model. I mean, it looks beautiful, right? Like something like this, but it's filled with really, small slivers here, fillets, and all of these sort of things, and it just causes the meshing program just too much trouble. A lot of times the meshing programs are actually pretty good, and so they will give you a mesh, but then the whole thing won't run. And so what happens is students will, they'll take this complex model, they say, oh, the easiest thing is just to hit mesh. They made it really easy for us. And then I'll throw it into a simulation. And most of the time what happens is it does not run, or it runs really slow. And so they'll go like the entire semester basically wrestling with this thing. And then near the last 2 weeks, they say, our thing won't finish. We can't get any results. What do we do? So that's typically the process, and so I'm trying to save you from that pain in the future. So what you want to do really is defeature it. Okay, so the whole defeaturing process, I mean, it's an art. There's different ways to do it. Things you want to look for: collapsing of short edges and sliver faces, hole and protrusion removal, joining of edges and faces and fillet, and round removal. We actually use virtual topology, remember, in the application before to do this, but this is actually modifying the CAD. Here's an example I had to do, and I just throw this example out because it was just on the top of my mind, but we do this a lot. Here, this is actually a hip replacement assembly. So it's like this is actually like goes into your body, you embed it into the bone somehow, and it has like a little screwdriver, and this is like to get around your hip bone or something. I don't exactly understand the configuration. And then this thing is basically like the surgeon would hold that and just like pound on it with a hammer. So it's a part they use for that. But in any case, you can see the CAD, this is what was given by the medical device company. I mean, you can look at the screwdriver. It's like a beautiful screwdriver, but it has really complex, all these different lines in it. The same way with this assembly here. Just really complicated, more complex geometry than you need to necessarily understand the overarching mechanics and physics and structural mechanics of a part. So there's the internal surfaces of it. It actually even had all the screw edges in it. So that was a really big problem the meshing program had. It actually, I got a mesh, but what we had to do is go from this to this. You see that all the fillets are removed, the screw edges and all that kind of stuff were all removed, and these features were removed. They actually, in SolidWorks, there are tools to actually defeature. If you build features up, so if you were build this model straight from SolidWorks, you can follow a history of your development and you can turn off certain features. And so you go back to basically something very primitive when you're first sketch. Here is some more details. I'm trying to remember what I wanted to do on that. Here is like one thing that the model wanted to do. So you have these really small, there was a fillet there, and so the meshing program tried to fill that in. As a result, it did a great job, but we get these small element edges, and you can see how small that element edge is. It's at least a half size smaller than the larger elements. And so that causes problems, especially when in a dynamic simulation that we're going to talk about here that has a small time step. In the end, we were able to get a stress result and still work in progress. The other thing you can do is shrink wrap. So another feature we use a lot in biomechanics, because we have all these really complex geometries and we need to kind of cover over some of those features that we don't want. So shrink wrapping is what you do. So by the way, this shrink wrapping capability is not really exist that I know of in Abacus. You have to actually go to ANSYS, the ANSYS mesher. ANSYS is another commercial software. That's called ICE MCFD, and we use that shrink wrap capability there pretty frequently, and it's really nice. In that, what you do is you basically take this complex geometry, you have all these different parts, and then you would actually imagine like a bubble around this part, and you collapse the bubble so it all has closed surfaces. So it's what they call a manifold surface, which means basically it's watertight. And when you do that, of course, you lose features. So you see you lose all these features, but still can be worked a little bit. It turns out for this problem, there was this complex wheel, this hub, okay? And what they really wanted to know about is that the hub stress. They wanted to know that. And so they needed boundary conditions. So instead of going full, they did one case where they did full resolution with all the geometry, and then they did a simplified model, and then they did a shrink wrap. Okay, and you can see when they computed the stress, so here's the picture of the shrink wrap version. When they computed the whatever loads, I'm not exactly sure what loads they put on this, but they did still resolve the hub fully. And you can see the stress distributions, this is von Mises stress, in the hub resulting from those three mesh configurations. So in the shrink wrap, you see that the maximum stress is pretty much ballpark with the full featured and the manually simplified. So this is just an awareness that you have to be aware of features in CAD. Be careful about that. What I tell students to do is take everything complex, basically go back to like a box. So let's say you have a complex engine part. And that would, in order to do that, you have to have all these cuts and everything. I actually start with the box. I get your material properties in. And then what I would do is do like cycles. So then you add another feature in, and then run a simulation, or add the next feature in, run a simulation. And you just keep doing that until you resolve. So what that does for you, it actually gets you a solution quick, starts to put bounds on max and mins, and you can start as you can add features pretty quickly in that then, and you won't lose a lot of time trying to get features to work. And when you have like a coarse model, then you can start to talk to your sponsor about it. So that's just some advice. All right, so let's end here on that little discussion. And next we're gonna quickly go over some higher order elements.